Hello and welcome to Lecture 2 of Circuits 1. Today we're going to be reviewing the passive sign convention briefly. It's very important. We need to be able to interpret the results of our analyses. This is really the only way to do that. We'll also talk about power generation and absorption and its relationship to the passive sign convention. Today we'll be introducing power sources officially. We've seen them briefly in some of the previous examples, but today I'll be talking about them in more detail. And finally, we'll talk about resistance, resistors, and Ohm's law. Related educational materials are in modules 1.1, 1.2, and 1.3. Okay, passive sign convention. For passive circuit elements, remember this is not for active circuit elements, we need to assume that the current enters the node that is at the higher voltage potential. Unless you do this correctly and are consistent about this, the results of your analyses will not be reliable. You will not know how to interpret the numbers that are coming out of your analyses. For example, if I have a passive circuit element with two terminals and I assume that the voltage potential is higher at this node than at this node, I need to assume that current is entering the upper node. It is perfectly legitimate to do the opposite assumption, that the voltage potential is higher at this node than it is at this node, but then you must assume that current is going into the lower terminal, which is equivalent to the assumption that current is leaving the upper terminal. Our assumed voltage polarity for a given circuit element is often used by adding subscripts to the variable name used for that voltage. Our notation is typically going to be to use two subscripts. We will use the order of those subscripts to denote the assumed polarity of the voltage on that element. The first subscript is going to indicate the higher voltage node. The second subscript is going to indicate what we assume to be the lower voltage node. For example, if we have a circuit element here which is connecting nodes A and B, if I say I want to look at V sub AB, I am indicating that I am assuming that node A is at a higher voltage than node B. This is the assumed voltage polarity. Conversely, if I say I'm working with V sub BA, I'm assuming that node B is at a higher voltage than node A is. All we've done by switching the subscript orders is to introduce a sign change. Since this is strictly a polarity change, V sub BA is just the negative of V sub AB. Another notation type of thing, voltages are often indicated as being relative to what is called ground. The ground symbol that I will use looks like this. It essentially provides a reference voltage, quite often assumed to be 0 volts. The 0 volts is simply an assumption in most cases. Voltages relative to ground are quite often not really referred to as a voltage difference, but they really are. They're a difference relative to 0 volts. Quite often, in this case, we use a single subscript to represent the voltage at a point. It's important to realize that you're not talking about a voltage at a point, you're still talking about a voltage difference. Voltage is defined as a difference between two spatially separated points. So if I have a circuit element here that has VAB, which is indicating a voltage polarity between nodes A and B, that's equivalent. If I assign node B to be ground, I will typically refer to the voltage difference between A and ground as just being V sub A. Okay, need to talk about power generation and dissipation. Circuit elements can either generate or dissipate power. Okay, power is dissipated or equivalently absorbed if the current enters the positive voltage node. If the current enters the negative voltage node, the power is generated or alternatively supplied. Okay, power is voltage times current. P is equal to IV. If power is absorbed, both of these numbers are positive relative to the passive sign convention. So if voltage and current are consistent with the assumed passive sign convention, that circuit element is absorbing power. Power is generated if this guy is negative. If one or the other of these has a negative sign relative to the passive sign convention, that circuit element is generating power. Okay? If they're both have the opposite sign to what is assumed, then power is still positive. It simply means that you've swapped both the voltage polarity and the current direction, but current is still entering the positive voltage node. Quick example. If I have a 3-volt difference here with 2 amps going into the positive voltage node, current is going into the positive voltage node. These agree with the passive sign convention. This element is absorbing power. It's absorbing 2 amps times 3 volts, 6 watts. Alternately, if I have a negative current going into the positive voltage node, I have an inconsistency with the current sign relative to the passive sign convention. So if I multiply V times I have a negative 2 amps times a positive 3 volts, which gives me a negative 6 watts. The negative 6 indicates that power is being generated. Okay, a couple quick examples that I want you to work out before I show you the results of what I am going to do with these problems. So pause the video, take a shot at them, come back, watch me do the problems. Okay, we want to determine the power absorbed by this circuit element. We have 2 amps going from bottom to top. We have a 3-volt difference where the polarity is, the voltage is higher at the upper node. Therefore, 2 amps is entering the negative voltage node. So this does not agree with the passive sign convention. Power is negative 2 amps times 3 volts. So this is 6 watts. It is actually generating power. So carry along the negative sign, negative 6 watts absorbed or positive 6 watts generated. I don't really care what you do with that sign. Another example. This circuit element, it claims to be absorbing 10 watts. I want to determine the current. If I assume that current is entering the positive voltage node, power is I times the voltage. This is 10 watts. 10 watts is being absorbed. That tells me that current really is entering the positive voltage node. So this current's going to be a positive number. So I is equal to 5 amps, or 10 watts divided by 2 volts. I need to talk about power supplies a little bit. I'm going to do a brief introduction now. We'll keep coming back to this topic for the next few lectures. Power supplies basically are an active circuit element. They provide a source of power to the circuit. This power or energy is coming from a source that's external to the circuit. That's important to remember. There are a number of different types of power supplies conceptually. Okay? We can have either voltage or current sources. We can have independent and dependent sources. We can also have ideal versus non-ideal sources. And we'll tend to mix and match these different categories. For the beginning, we'll just kind of briefly introduce some of the basic things. We'll stick with just ideal sources. We'll talk about non-ideal sources a little bit later on. The first type of power supply I'm going to talk about are independent voltage sources. There are a number of symbols used on electrical circuits to indicate an independent voltage source. This is the one that I will probably default to most often. It's a circle with a plus and minus sign indicating the positive voltage polarity. This one here is a voltage V of t, which is assumed to vary as a function of time. This symbol, often used to denote a battery, generally indicates a constant voltage value. Again, the polarity has to be given for active voltage sources. This upward arrow simply indicates a positive voltage, V sub dd, relative to some reference voltage. A downward pointing arrow generally indicates a negative voltage relative to the same reference. I will generally default to this symbol to do even constant voltage values because I generally consider a constant value to be a special case of a time varying value. One thing I need to point out, whatever voltage is specified here in this symbol is provided to the circuit regardless of anything else that's going on. The specified voltage is provided to the circuit. That means that these guys can provide any amount of current to the circuit that they are connected to. There is no limitation on the power that they can supply if you hook this up to the right circuit. Another type of power supply we'll be dealing with are independent current sources. I'll typically only use this symbol to denote an independent current source. A simple circle with an arrow in it indicating the direction of positive current. This current can be a function of time as indicated here or a constant value. I'll use the same symbol for both. This type of power supply provides this given current, whether it's a constant or a function of time, regardless of whatever voltage difference is put across this current source. As we see later, that can cause some potential problems with power delivery. If we need to provide an infinite voltage here, this guy will put out infinite power. Similar kind of slide as the previous one. If I have a current source that is providing me with a constant current I sub s, and I give myself a voltage difference across here, I can plot the voltage versus current. The current is a constant. I don't have any information about what the voltage is. I can have either a positive voltage difference here, in which case this guy is generating power, or I can have a negative voltage, in which case this guy is absorbing power, depending upon what the circuit is doing that this is connected to. Okay, the ideal power source models that I've been talking about so far do have some limitations. One of the main ones is that they potentially can provide infinite power, which is non-realistic. The voltage sources, they provide a specified voltage regardless of anything else that is going on in the circuit. If the circuit wants to draw infinite current from that power supply, the power supply will give the circuit infinite current. Since power is the product of voltage and current, this means that the power supply can provide infinite power to the circuit. Likewise, with the ideal current sources, they provide the specified current regardless of whatever the voltage is that the circuit is demanding of them. If the circuit demands an infinite voltage, the power supply can provide infinite power. Now, I don't necessarily know of anything that can give me infinite power, so these models can be unrealistic. Okay? In these particular cases, they are not good models of the physical reality of the world. Later on, we'll introduce some modifications to these models that will provide a more realistic power supply model under these conditions. Another category of power supplies that we deal with fairly often are dependent power supplies. This simply means that the power delivered by the power supply is dependent upon something else that's going on in the circuit. Our power supplies can deliver either current or voltage. We can use a current or a voltage elsewhere in the circuit to control the power that is delivered by the supply. That gives us 4 possible combinations for types of dependent power supplies. We can have a voltage source which is controlled by a voltage, or a voltage-controlled voltage source, VCVS. We can have a current-controlled voltage source, in which case the source delivers a voltage, but that voltage is dependent upon a current somewhere else in the circuit. Likewise, we can have a voltage-controlled current source or a current-controlled current source. We'll talk more about these later on in this class when we have some physical devices that we can use to implement these. This is a voltage-controlled voltage source. My diamond-shaped box indicates that this is a dependent power supply. The voltage that it is putting out is some value K times V1, which is a voltage elsewhere in the circuit. So I'm using a voltage to control this voltage source, hence the terminology. For a current source, I still use a diamond-shaped box. However, the arrow inside that indicates the direction of the current flow from the source. This is a voltage-controlled current source. The value of this current is related to V1, which is a voltage source at some other point in the circuit. Resistors will be our first passive circuit element. Our circuit symbol is this jagged line. The R is the resistance of this resistor. Its units are ohms. All of our passive circuit elements are going to be governed by some voltage-current relationship. For a resistor, that relationship is called Ohm's law. The voltage is the resistance times the current through the resistor. So if our voltage across the resistor is V of t is R times whatever I of t is. Now previously I plotted some voltage-current relationships for sources. We'll be doing that a lot. The plot of voltage versus current for a resistor is simply a straight line. Okay, V is R times I, so the slope of this straight line is the resistance R. A couple of quick things to note about resistors. Resistors can only dissipate energy. You cannot store energy in a resistor. So any energy that goes into these guys gets dissipated as heat typically. The other thing to notice about these is that the voltage-current relationship is algebraic. These two things are related. If you have an algebraic voltage-current relationship, you can't store energy. We'll talk more about that when we talk about our energy storage elements, capacitors, and inductors. Okay, since resistors only dissipate power, we can develop some special purpose power dissipation rules for resistors. Quick review, Ohm's law says voltage is current times resistance. I can rewrite that as current is voltage over resistance. Our definition of power was P is V times I. We can combine these two things. For example, we can substitute I of t for V over R. Then we can expand this so that the power dissipated by a resistor is V squared over R. Likewise, we can write this purely in terms of current by substituting voltage as R times I of t. Then the power dissipation is the resistance times the current squared. This, and this will all give identical results for the power dissipation of a resistor. Quick example. Try this one on your own, then I'll come back and do it for you. We want to determine the power and whether it is absorbed or generated by this resistor. Okay, resistors can only absorb power. You can never use a resistor to generate power. That means that the voltage-current relationship for a resistor always obeys the passive sign convention. So current, I, is always going to be entering the positive voltage node for a resistor. So I can calculate a current through this by Ohm's law. So V is R times I, so I is equal to V over R. So I is equal to 2 volts over 3 ohms is equal to about 0.67 amps. Power is I times V, so this is 0.67 amps times the voltage, which is 2 volts. 0.67 amps times 2 is 1.33 watts, approximately. There's an easier way to do this problem for a resistor. You're given the voltage difference. The power can be determined directly from the voltage across the resistor. So P, we can use our relationship V squared over R. Voltage is 2 volts squared over 3 ohms. So this is 1.33 watts again. Just for kicks, once we'd calculated the current previously, we could use that current directly to get the power dissipation for this resistor. So before, we had I is equal to 0.67 amps. We did that previously. Power is I squared times R for a resistor, so 0.67 amps squared times 3. 2/3 squared is 4/9, which is 1.33 once I multiply it by 3. Okay. Any of those things will give me the same result. Take a look at what you're given and use the simplest approach to determine what you're after. Okay, our final topic on power for the moment is going to be talking about conservation of energy. In any electrical circuit, the amount of energy absorbed is the same as the amount of energy generated. Mathematically, if we sum up the power contribution from all the elements, we have to get 0. And remember that if power is absorbed, that's a positive number. If power is generated, that's a negative number. That's how we can make these powers sum up to 0. Some of them are negative, some of them are positive. The overall contribution has to be 0 from the entire circuit itself. Quick example of this. I want to determine the power absorbed or generated by this voltage source if I'm given a couple of passive elements and a current source. Okay, I'm given the voltages and the currents for both of these passive elements. I'm also given the voltage and the current for that current source. We can use that to determine the power generated or absorbed by this voltage source. Give it a try. Come back and watch me do it. Okay, for shorthand, I'm going to call this element number 1, this element number 2. The power of element 1, I have 2 amps going into the positive voltage node of a 1 volt difference. So this is 2 amps times positive 1 volt. This gives me 2 watts. That's positive. This guy is absorbing energy. Element 2 has 1 amp going into the positive voltage node of a 2 volt difference. So the power of element 2 is 1 amp times positive 2 volts. That's 2 watts, also absorbed. This source here has 3 amps. It is going into the negative voltage node of a 2 volt difference. So the power absorbed or generated by the 3 amp source is negative 2 volts times 3 amps is minus 6 watts. Okay. So if I add up all these power contributions along with the power of V sub s, so P sub Vs plus P1, which is 2 watts, plus P2, which is 2 watts, plus P3, which is minus 6 watts, that has to sum to 0. 2 and 2 is 4, minus 6 is negative 2. Take that to the other side, so P sub Vs is 2 watts. This voltage source is actually absorbing power. The current is coming in the positive voltage node. That concludes lecture 2. Next time in lecture 3, we'll do a quick review of some of the power stuff, absorbed power, generated power, conservation of power. Then we'll actually introduce a couple of analysis methods, Kirchhoff's current law and Kirchhoff's voltage law. I've been mentioning that as long as we stick to the passive sign convention, you'll be able to interpret your results from your later analyses correctly. We now get to do some of the later analyses. So we'll spend probably the next couple lectures talking primarily about the analysis methods. These will be biggies. You'll need to know them really well later on in the class.